Welcome to the deep dive.
Wow.
Today, we're going to be tackling a real giant in the world of mathematics, David Hilbert.
Oh yeah, Hilbert. Yeah.
Yeah, we're going to be exploring his key contributions and his role in the famous foundations of mathematics debate,
Right.
and why it all matters even today.
You know what makes Hilbert so interesting is he wasn't just trying to solve problems. He was really trying to understand the structure of math itself.
Yeah,
Asking questions like, how do we know if math is even true?
right.
What are the building blocks? What are we working with here?
Questioning the rules of the game that everyone else was just playing.
Exactly.
Yeah. So our main source for this deep dive is a fascinating National Geographic biography of Hilbert,
Oh, cool.
which really gets into his work, especially in geometry and these foundational issues.
I mean, these foundational issues are so interesting because they really point to how do we know anything for certain?
Yeah,
You know, math is often seen as this bedrock of truth.
right.
But Hilbert really challenged us to dig deeper.
To examine those assumptions.
Exactly.
Yeah. All right, let's start our journey in Königsberg,
Okay.
Hilbert's birthplace.
All right.
And this wasn't just any town. It has a rich mathematical history. Think Immanuel Kant
Oh, wow.
and the famous Seven Bridges problem.
Right, where you try to cross each bridge only once.
Yeah, have you ever heard of that one?
Oh, yeah, it's a classic problem.
Yeah.
And Königsberg's layout actually sparked a lot of early mathematical thinking about networks and topology.
Interesting.
So you could say the city itself kind of influenced Hilbert's early exposure to mathematical ideas.
I love that. So young Hilbert, he was already making waves solving complex algebraic problems.
Yeah, he was a prodigy for sure.
But here's where it gets really interesting. He shifted gears and dove headfirst into geometry,
Really?
becoming a champion of something called the axiomatic method.
Okay, so the axiomatic method is all about building a logical system from a small set of basic assumptions.
Okay.
It's like you're laying the foundation for a house. Hilbert was all about making sure that foundation was solid.
He wanted to make sure those mathematical houses wouldn't collapse. And Hilbert wasn't just a geometry guy.
Oh, okay.
He had expertise in algebra and number theory, analysis, you name it.
Wow, so he had a really broad understanding of mathematics.
Yeah, it's like he was preparing his brain for those foundational issues he'd tackle later on.
That's fascinating. It makes you wonder if his broad knowledge allowed him to see connections that others might have missed.
Maybe like looking for that unifying framework. Okay, so let's fast forward to the late 19th century. The world of geometry was getting a little shaken up.
Uh-oh.
Mathematicians were grappling with these different types of geometry, Euclidean and non-Euclidean, and it was really changing the way people thought about math.
It's like discovering that the Earth isn't flat, right?
Yeah,
I mean, non-Euclidean geometries kind of blew everyone's minds
totally.
because they challenged those long-held assumptions about the flat Euclidean system.
Right. And Hilbert jumped right into this fray, working on axiomatizing geometry.
So he was trying to bring order to this new world of geometry.
Yeah, he went beyond Euclid's Elements.
Okay.
You know that ancient Greek text on geometry?
Right, one of the most famous math texts of all time.
And created a more rigorous and complete set of axioms.
So it's like he was creating a more powerful, updated version of Euclid's system.
Yeah, like creating a more powerful operating system for geometry.
I like that analogy.
Mhm.
But he wasn't just trying to tidy things up. He was after three very specific properties in any axiomatic system:
Oh, really?
independence, consistency, and completeness.
Okay, break those down for me.
All right, so independence means each axiom stands on its own, right?
Okay.
And consistency means no contradictions can arise within the system. And completeness means that all true statements can be derived from those axioms.
Wow, so he was incredibly meticulous,
Oh, yeah,
like creating the ultimate rule book for geometry.
exactly. But he didn't stop there.
Oh, no.
Hilbert also introduced this idea of metamathematics, which is
Yeah.
basically thinking about mathematics itself.
So like stepping outside the game to analyze the rules and strategies.
Yeah. It allows us to explore what's possible within any mathematical system.
It's like the philosophy of math.
Exactly.
Yeah, and here's a great anecdote that illustrates his thinking. There's this story about Hilbert saying he could call anything points, lines, and planes,
Really?
as long as they fit his axioms. He even used tables, chairs, and beer mugs as examples.
Wow, that's kind of mind-blowing.
It shows how focused he was on the abstract structure rather than the physical objects themselves.
He was emphasizing the formal structure over any particular interpretation.
Now imagine this. The year is 1900. The setting is the International Congress of Mathematicians in Paris.
Ooh la la.
Hilbert, at the peak of his career, unveils a list of 23 unsolved problems.
It's like he threw down the gauntlet for mathematicians all over the world.
A challenge for the entire 20th century. But it was more than just solving problems. It was a statement about the nature of mathematics itself. He seemed to be saying, hey, real progress comes from tackling the toughest questions head on. And these problems covered a huge range of topics: foundations of math, physics, number theory, algebra, you name it.
It speaks to his incredible vision. He saw how all these seemingly different areas of math could be interconnected,
Yeah.
and how progress in one area could illuminate others.
Okay, let's dive into a few of those problems. First up, the continuum hypothesis. Get ready for this one. It asks if there's a set whose size falls between the integers and the real numbers.
So it's about infinity, right?
Yes.
Are there different sizes of infinity?
Sounds simple enough, but it opened up this Pandora's box about infinity and set theory.
Questions that still haven't been completely resolved.
It's still puzzling mathematicians today. Next, we have the Riemann hypothesis. This one's all about prime numbers, those numbers only divisible by one in themselves.
Prime numbers, the building blocks of all numbers.
It's a super deep question, and guess what? Still unsolved to this day. Hilbert was clearly looking to push the boundaries of number theory.
I mean, the Riemann hypothesis is considered one of the most important unsolved problems in all of mathematics.
Really?
Absolutely. Understanding how prime numbers are distributed is crucial for so many areas of math.
Wow. And last but not least, we have axiomatizing physics.
Okay.
Hilbert was essentially asking if we could describe the laws of physics, like mechanics or thermodynamics, using the same rigorous axioms he used for geometry.
It's like he was searching for a universal language of science.
He was searching for the underlying code of the universe.
That's a great way to put it.
Yeah.
And his interest in axiomatizing physics really reflects his deep belief in the power of the axiomatic method.
Yeah.
He really wanted to bring that same clarity and rigor to scientific theories.
It's almost like foreshadowing, you know?
Exactly.
Like all the later attempts to unify physics under a single framework.
Yeah, like string theory and things like that.
So Hilbert was passionate about bringing that axiomatic rigor to physics, just as he had done with geometry. But he wasn't just the theorist.
Right.
He was also a master of developing practical tools.
He was great at both, right?
Hmm.
Abstract thinking and applying those abstractions to concrete problems.
Yeah.
That's a rare combination.
One of the areas he really dug into was the calculus of variations.
Okay.
This involves finding the best solutions to problems, and it has applications everywhere, from mechanics to optics. To help you visualize this, think of a stretched membrane, like a drumhead,
Okay.
and how it naturally finds its equilibrium shape. The calculus of variations helps us understand those kinds of problems.
That's a great example. So it's all about optimization, right?
Yeah.
Finding the most efficient solutions to problems.
And he also worked on integral equations,
All right.
which are like a different way of expressing mathematical relationships. Hilbert saw these as incredibly useful tools for solving complex problems in physics.
Integral equations can be a really elegant way to solve certain types of differential equations.
And here's the mind-blowing part. His work on integral equations laid the groundwork for some of the math used in quantum mechanics, even though quantum mechanics hadn't even been developed yet. Talk about foresight.
I mean, that shows just how deep his understanding of the underlying structure of these fields really was,
Yeah.
that his work would have such far-reaching implications.
Incredible.
Yeah.
So we've seen how Hilbert tackled geometry and physics with this axiomatic approach.
Yeah.
But now we're moving into like a different arena, the philosophical foundations of mathematics.
Right.
This is where the crisis of foundations was really brewing.
Oh, yeah.
A real battle of ideas about the nature of mathematical truth.
This goes way beyond just mathematical proofs.
Yeah.
It gets at like how we know what we know,
Yeah.
questioning the very assumptions that math is built on,
Right.
challenging this idea of absolute truth in math.
Like, imagine mathematicians arguing passionately about whether math exists independently of us or if it's something we just invented.
Yeah, and a real philosophical cage match.
Totally. So let's meet the key players in this debate.
Right.
First, we have the Platonists.
Okay.
They believed that mathematical objects, numbers, shapes, and so on exist in some perfect realm
Okay.
outside our physical world.
Right. So, like, there's this cosmic library of math out there,
Yeah.
and we're just discovering its secret.
It's a really compelling view for a lot of mathematicians.
Oh, yeah.
Because it suggests that mathematical truth is objective and eternal.
It just feels right,
Yeah.
when you're working on these abstract concepts.
Then we have the logicists.
Okay.
They were all about reducing math to pure logic,
Right.
like building a house out of the simplest possible bricks.
Yeah.
They wanted to show that every mathematical truth could be derived from just a few basic logical principles.
They were all about clarity and rigor.
Yeah.
Trying to, like, get rid of any ambiguity in math.
Make it super solid.
Yeah. By grounding it in logic.
And lastly, we have the Intuitionists,
Okay.
the rebels of the math world.
Right.
They rejected this idea of infinite sets and non-constructive proofs.
So for them, math had to be built step by step,
Yeah.
with each step, like, verifiable and clear.
Yeah, so where did Hilbert stand in all of this?
All right. Where did he fit in?
He was firmly in the axiomatic camp.
Okay.
He believed that math was a formal system
All right.
and that its consistency could be proven like a perfect machine with no loose parts.
So he's a formalist,
Yeah.
trying to establish math as this system of rules and symbols,
Right.
independent of, like, intuition or external reality.
But this is where things get really interesting.
Oh.
Enter Lutzen Egbertus Jan Brouwer.
Try saying that 3 times fast.
I know, right? The champion of Intuitionism.
All right, so Hilbert and Brower, they clashed
Oh, yeah.
in this, like, epic intellectual battle.
It wasn't just an academic disagreement. It
No.
was like a struggle for the soul of mathematics.
Right. They fundamentally disagreed about what math was.
And how we can know if something is mathematically true.
Exactly. And the methods we can use to figure that out.
And it got personal.
Really?
Hilbert felt betrayed when his own student Hermann Weyl sided with Brouwer.
Oh, wow. So it's like a family feud in the world of mathematics.
Yeah, exactly.
Fantastic.
One of the big sticking points was Brouwer's skepticism about the law of excluded middle.
Okay, remind me what that is again.
So this is the core logical principle that says a statement is either true or false.
Right. True or false?
There's no middle ground.
Okay.
Hilbert took this for granted.
Yeah, makes sense.
But Brouwer challenged it, saying it didn't always apply, especially when you're dealing with infinite sets.
So that's a fundamental challenge to classical logic.
Undeterred by all these philosophical disputes, Hilbert set out on his very ambitious program.
All right, what was he trying to do?
He wanted to prove the consistency of arithmetic using what are called finitary methods, essentially showing that you couldn't derive any contradictions from the basic rules of arithmetic.
So trying to make sure that the foundation of math is totally unshakable?
Yeah, he envisioned this grand system
Right.
where all mathematical truths could just be mechanically derived.
It's like a giant logical machine cranking out theorems?
It was a bold vision,
Yeah.
but then plot twist.
What happened?
A young logician named Kurt Godel entered the scene.
This is where things get really interesting.
In 1931, Godel dropped not one but 2 bombshells.
Oh.
His incompleteness theorems.
Incompleteness theorems.
Yeah.
That's a pretty ominous name.
The first theorem basically stated that any sufficiently complex formal system
Okay.
will always contain true statements that you can't actually prove within that system.
That's wild.
It's like saying there are some mathematical truths that are forever beyond the reach of our logical tools.
Right. So Gödel's basically saying there are limits to what we can prove.
And the second theorem was even more mind-blowing.
Okay, what was that?
It said that no consistent formal system can prove its own consistency.
Wow.
It's like saying you can't use the system to validate itself.
Right. You need something outside the system to vouch for it.
So imagine the shockwaves that went through the math world.
I bet people were freaking out.
Hilbert's dream of this perfectly self-contained and secure foundation for math was shattered.
So it's like finding a crack in the bedrock of mathematics itself.
Yeah.
That's pretty unsettling.
But you know what?
What's that?
Gödel's theorems didn't destroy mathematics.
Oh, good.
They just forced a fundamental reevaluation of its foundations.
Right.
They led to this deeper understanding of the limits of formal systems and the really crucial role of human intuition and creativity in mathematics.
So it wasn't the end of math, just a new beginning.
Exactly. So it seems like Godel threw a real wrench into the works.
Yeah, you could say that.
Hilbert's dream of this perfect self-contained mathematical system kind of went up in smoke.
Yeah, his theorems were a major shakeup. They showed there are these inherent limitations to what formal systems can actually achieve. But, and this is important, it didn't invalidate all the work that had come before. you know.
Okay, that's a relief.
And it didn't stop mathematics from moving forward either.
So math didn't just crumble into a pile of contradictions.
Not at all that. Mathematicians are a pretty resilient bunch.
Yeah.
I think Gödel's theorems just force a shift in perspective.
Yeah.
It's like we thought we were building this grand, flawless cathedral of mathematics,
You're right.
but Gödel showed us there were some hidden quirks in the architecture.
Okay, I'm starting to see the bigger picture here. So instead of despair, Gödel's theorems kind of sparked a new kind of exploration.
Exactly. It became less about finding this single absolute foundation for math and more about understanding the different ways we can actually build and explore mathematical systems, knowing that there will always be some unprovable truths kind of lurking out there.
So we traded in our quest for absolute certainty for a deeper appreciation of the mysteries of math.
Yeah, you could put it that way. And remember, Hilbert's influence went far beyond this specific debate.
Yeah.
I mean, his emphasis on rigor, his axiomatic approach, his drive to tackle those big fundamental questions,
Yeah.
those had a lasting impact on how mathematicians work.
So even though his grand vision didn't pan out exactly as planned, his fingerprints are all over 20th century mathematics.
Absolutely. He was a catalyst for a whole new era of mathematical thought, and his legacy continues to inspire mathematicians today.
All right, so after all this deep diving, I have to ask, what's the takeaway for me? Why should I care about this whole foundational crisis thing?
That's a great question.
Yeah.
It all boils down to this understanding the foundations of mathematics isn't just about abstract theorems and proofs. It's
Yeah.
about understanding the nature of knowledge itself.
Yeah. Okay.
What can we know with certainty? What are the limits of our reasoning? How do we build reliable systems of thought? These are questions that have implications way beyond mathematics, touching on philosophy, science, even our everyday lives.
Wow, I never thought about it like that. So Hilbert's journey, even with its bumps and detours, it helps us understand how we think and how we build knowledge.
Exactly. And it leaves us with some pretty mind-bending questions to ponder. If Gödel showed us that even mathematics can't prove its own consistency, where does that leave us? Does it mean all knowledge is ultimately uncertain? Or does it point to something even more profound about the nature of truth and understanding?
Okay, now my brain is officially doing backflips. That's definitely something to chew on. Thanks for taking me on this deep dive. It's been a wild ride.
It's been my pleasure. And remember, keep questioning, keep exploring, and keep diving deep into the fascinating world of mathematics.
I will.
There's always more to discover.